All right, this is homework number 6, question number 3. And I was getting a few questions on it. It looked like it was just a little bit of a tricky one and kind of a unique setup. So I'm just going to read it out and then we'll discuss. So here I drew a square loop. It's placed in a magnetic field. That's what it's going in, out of the page. That's what that little circle dot is. And the rate is given and it decreases. So that's a special word right there, decreases. That tells us that we're going to treat that as a negative over a unit time. So that means that we have a delta B over some change in time equals that value, but negative. So it's 0.3, right? So that's given. And that negative right there is because it tells us we're decreasing. All right. So the resistance per unit length of the wire is given. And again, that's a per unit length. So let's first ask, it's first asked to determine the induced EMF. So what's our equation we're going to use here? Induced equals, obviously, it's going to be that minus n, but we know there's only one loop. So we can just, I'm just going to not even write n, right? So it's going to be minus, have our looks over, sorry, I have my notes right here, over some change in time. All right, so at this point, we remember our equations. What is this guy equal to? That equals V times that area, cosine theta, where this theta is going to be equal to 0 degrees. Okay. Oh, I hope this isn't flipped. Okay. Well, hopefully we'll see when the recording comes out. Right. So cosine is equal to 0. So that just cosine 0 equals 1. So we can just kind of ignore that. So we can simplify this expression as delta B A over delta T. But obviously the area is not changing. It's constant. This thing's not like growing or anything. And we know that the area equals S squared, where like I'm choosing S for side, where S equals 3 centimeters or 0.03 meters. So that means we can pull, oh, sorry, S. So we have minus S squared times some delta B over delta T. And then both of these things are given. So we just end up having to plug in 0.3 squared minus times that. And then, our negative here will cancel out with this negative, and that's very nice for us. And it comes out, I don't know, some very small number. I wrote it down here. Is it 2.7 times 10 to the minus 5 volts. All right, so the big thing here is that we're working with this delta B over delta T that's given, and we're just going to cancel out the negatives. And the negative exists here previously because we're told that there's a decreasing. Okay, so at this point, let's move on to part B. I'll work on part B over here in this corner. Can I do that right here? Yeah, so do B in this corner. So what do we ask for again? Let's see. We want to determine the magnitude and direction of the induced current. So the first thing we do is establish what equation we're going to be using. And as you expect, sorry, I'm going to walk around this way. As you expect, we're going to be using I'm just writing induced on each thing because we know that it's going to induce some kind of current, right? Also what we're solving for. And then R. And notice what I'm going to write here. I'm going to write R total. And that's because there's a resistance that exists on each one of these sides. So that means we need to first, how should I say that? Actually, let me do it in the steps. So we're going to write R total here. That means there's a resistance relative to each side. So what we need to do now, rearrange the equation. We have I induced equals that R total, that resistance total. So we're recognizing every single side. This is just one wire. This is a multi-side situation over that EMF, right? Oh, wait. I think I messed up here. Yeah, this is flipped. Like that. Okay, sorry about that. At this point, we just solved for this value, but now I'm just gonna write it real quick. 0.7 times 10 to the minus 5 volts. What do we write for this R total? So we're given the resistance per unit length. So if we multiply it by the total length, that being 4S, we'll be able to get the resistance just by itself, right? Because those units of length will cancel out. So 4, that's for it's times 4, 0.3 times 0.0. Like that. All right. Let me just double check which one of those was given. Yeah, okay. So we're given this is the resistance per unit length. By multiplying it by the total length, that being 4 times 0.03, that total length of the sides, we now cancel out that meters, right? Because it's like 0.3, and then it's like that resistance per meter. And we multiply it by the total length. I'm just going to call it meter tote. Those meters will cancel out. So we're just left with the resistance. At this point, we have enough to solve for I induced, and that comes out to be, let's see if you can still see, 0.00075 amps. And counterclockwise. You might have guessed already just from this diagram. Okay, hope that helps. Quick video. Let me know if you have any questions. Again, messed up here, E induced divided by that R tote.